method on it, what will actually happen is C++ will compile this directly into an ordinary function call. So there is some code for the method f on A, and this method call on this pointer to an A is just directly calling that with the object passed in as an argument. And that's it. Nothing else happens. So this is one of the things that, hopefully everyone here who's written C++ knows. When it's an in-person lecture, I ask, who here has programmed with C++, who hasn't. I get some hands. I get a lot of people who have never programmed in C++ before. And this is one of the very first things you'll run into if you're trying to write C++ for the first time and you've worked in other object-oriented languages and you're not, you're familiar with this dynamic dispatch being everywhere. And then you go to C++, you write the obvious code, you write these methods, and it doesn't work. It always goes to A. In this example. And that's because that's what C++ said, right? C++ said, hey, I don't want to pay for dynamic dispatch if I can get away with it. So if you write a method and you don't tell me anything about it, then I'm just going to go straight to the implementation that I know statically is going to be called in this case. Because at this function call here, I know that PA is a pointer to an A. So I know exactly what F this is referring to, and therefore I can compile it into an ordinary function call. Okay, please shout questions as you go, but I'm gonna keep going. So the next thing that C++ has is an inheritance. So how does this work? Well, in C++ you can inherit from classes. C++ uses the colon syntax. So when I say class B colon A, that means B inherits from A. And so if I have a bunch of classes and they define a bunch of fields, and they define a bunch of methods, when I, for example, allocate a class C, I get an object that just simply has all of these fields concatenated together. This should sound familiar. This is how, for example, Simula did it. But one important thing is that when you access these fields, the compiler knows exactly where the fields are. So there's no lookup procedure that, for example, you had to do with when we were modeling objects as activation records. C++ is like, well, C is only ever inheriting from B, is only ever inheriting from A. So I know exactly that, well, the field A has to live in the first spot, and the field B has to live in the second spot, and the field C has to live in the third spot. So what C++ will actually do is it'll just hard code the offset when you access a member. There's no need for any indirection because, well, why would you need it? You know exactly where it is. So once again, don't pay for functionality you don't need. And this doesn't seem very problematic, and it isn't until we start talking about multiple inheritance. Okay, hopefully no questions here. All right, so okay, let's get to it. So you're a hapless new user of C++, and you wrote a bunch of methods, and they didn't work, and you're like, why aren't they working? Why isn't my subclass method being called? You Google on Stack Overflow and say, oh, you have to use virtual methods to actually get the behavior you wanted. So let's imagine that we've got this class A, and this time I've turned all of the methods into virtual methods. So virtual F, virtual G, virtual H. And then I inherit from B, A, overriding G, and then I'll inherit from the C, from B, giving me C, and this time I'll override H. And now C++, you've asked for another feature, and it's not going to come for free. C++ has to do some work to actually make things all work out. And so the work in this case is in the form of a virtual table. So let's step back for a moment and talk about sort of what the problem we're trying to solve is. So when we allow for functions to get overridden in this way, we basically don't know what function we're going to call when we now invoke, say, a f on a pointer to an object of type A, because it could be going to the implementation of f that I gave on A, but it could also be going to any implementation of F that was provided by any of the subclasses. Actually, I shouldn't have said F because we don't even override F in this example. So we need to remember what the actual implementations should be. And so when I did the small talk lecture, I was like, well, we just, go to the class of the object, which, that's a pointer. We go to the class and then you look up the method there and that tells you what method you want to do. But no, we're C++, right? We're cool. We don't want to have to go through all of this pointer indirection. We want the cheapest, simplest possible implementation that we can do that the hardware is going to support. So what C++ does instead is they say, hey, here's what we're going to do. For every virtual method on a class, we are going to define a vtable, short for virtual table, containing function pointers to the implementations that I want to use here. So I got my object C, right? It's got all the fields, A, B, C, but at the very top, it's got a V pointer field. And this V pointer field points to another table that contains pointers to the object, the function implementations. So in the case of C, the F field points to A::, F because it wasn't overridden. The G field points to B::, G because B overrode the value of G. And the the H field points to C::, H because C overrode the meaning of H. And so this vtable tells us what the implementations of the object should be at any given point in time. So for example, if I have a pointer to a C object and I call the virtual method G on it, what the compiler will transform this into is it says, hey, give me my object, look at the vtable, find the function pointer that's in the G slot, in this case hard-coded to 1, because once again, we do know what all the methods are, even if we don't know what order they are. Even if we don't know what the implementations of these methods are, we know what order they're going to be. That's statically known when I'm talking about the C object. It's F, G, and H. So I look at the G field, and that is the function pointer that I'm actually going to use to do the call in question. Questions so far? So just to step through this, so we've got our object, we look up the vtable, we offset into the G entry, and then we actually call the function in question. Okay, hopefully there was some C++ in prior classes, so this should be familiar. Okay, so this is a clear example of implementation affecting semantics, right? So C++ has these two concepts, non-virtual methods and virtual methods. Why does it have two separate concepts? Well, it's because they wanted to, offer you the two different implementation strategies because they have different performance characteristics. So the non-virtual method call compiles to a direct function call. It's just syntax sugar for writing a regular function call. Whereas a virtual method indirects through the vtable so that you can override, so that you can redefine the meanings of operators. And of course, the direct function call can't be overridden. You can't actually redefine the function. Well, you can overload the function so that there's another overload that's available. But once again, this is still relying on the statically available type information at this point in time. This is why C++ will actually let you, if you have a non-virtual function, override it in a subclass, but any sort of linter tool, I think even it's built into the warnings in the compiler, Worth Its Scratch, will warn you, hey, you probably didn't want to do this. And that's because if you had a function of type C, if you had a class of type C, you would indeed hit the override. But if you if you cast the C object into the parent class A, and then you call that method, you'll get the A implementation because it's just going to call exactly what the type says it should call at that point in time. Questions. Let me see. Yeah, so this is just going through that example that I just said. So when I have a virtual method and I have a object whose name is B, then when I assign it to an A* pointer and I call F on it, I still get to the B implementation. I still print out child in this example because I went through the V table to actually find the implementation. If I do it this way, right, no V table, then when I do the F function call, it goes straight to the A implementation because the dispatch is done by types. This is how overloading in general works in C++. You like look at all the types of the things in question, you find the overload that matches the types best, and then that's the actual function call you actually call into in that situation. Questions? All right. I'm repeating myself a lot today. I'm getting ahead of myself with these slides. So here's a comparison between the object models of JavaScript and C++. So in JavaScript, we said that, JavaScript is a prototype-based language. So every object has some prototype that says basically how various things should be implemented if they aren't available on the object itself. So in the example that I had before, where I had A, B, and C each inheriting from each other, that would have corresponded to this object pointing to the C implementation, but that would in itself point to the B's implementation, which would itself point to the A implementation. And so when I call, say, F, I have to look for it in C. It's not in C. Then go to the prototype, look for it in B. It's not in B, and then finally look for it in A, where I get it. And in C++, none of that happens, right? We can go straight to the location we want in the V table. By the way, if you are running JavaScript in any real environment, there will be a tracing JIT, which will be trying to, optimize this into something more efficient. But like sort of naively, JavaScript doesn't have that efficiency. It has to work hard to recover it. Whereas by C++, it's by construction. It's just exactly how things are designed. Oh, it gets even worse, by the way, because in JavaScript, you don't even know what all the fields on the object are going to be. So in general, these have to be represented as dictionaries. So you have to do a hash table lookup. Whereas in all of these cases in C++ is a statically typed language. That means we know where everything is at compile time. And so we can turn everything into direct offsets when we compile C++. One of the reasons why C++ is so fast. Okay, so there's one last thing that I want to say about the objects in question, which is that when we are dealing with an object like, say, of class C, I gave you the object layout, right? I said, well, there's a V pointer at the top, and there's a bunch of fields, and the V pointer itself points to a V table. But actually, right, like this is just what you know about because you're a C object. C could have been extended into another subclass, which could have added more fields and could have added more virtual methods. So in fact, we don't know anything about what's going on beyond the edge of the object in question. It could be arbitrary other data that sort of was brought in by another subclass. All we know is that C has this particular physical layout, and we can rely on the things in this layout being there, right? So I can make calls to F, G, and H on C because I know, well, there will be vtable entries at these locations. Of course, it might not be C::H, it could be D::H, but that doesn't matter to me, right? I'm just going to call whatever function pointer is stored there. To make this super concrete, right, when I cast a pointer to C to a pointer to A, I forget all the stuff that I know about C, right? So all I know is, well, there's a field named A, and there's a vtable entry for F. And you can see that C was able to just add on some extra fields in both cases, but if you sort of close your eyes and forget about everything you knew about C, well, you've still got a perfectly valid A object in this situation. Questions? What are your questions? So to summarize, virtual method calls mean invoke a function pointer at a fixed offset on the vtable. And you should remember this because now we're going to talk about multiple inheritance, and this is going to like be stuck in our brain, right? We're going to be like, how do we do multiple inheritance? Well, we already defined virtual method calls to be doing this. So now we're going to have to work really hard. Okay. So let's talk about multiple inheritance. Okay, so the first thing I have to answer is why the heck would you be interested in multiple inheritance? And indeed, if you read most modern C++ style books, they'll tell you, hey, multiple inheritance is bad. You should avoid using it, when you can. And this is by and large true. And if you don't need multiple inheritance, you shouldn't use it. That being said, there's two things that I want to say. So one is that multiple inheritance is just a tool. It's a tool for setting up object layout in some particular way. So if you're writing some code and you're like, oh, I want my objects to be laid out in this way in memory, multiple inheritance might be the right thing to use because it just directly gives you the thing you want to do. The other point that I want to make is that I'm here to sort of teach you about like programming languages concepts. And I want to talk about multiple inheritance because it's a really interesting case study of design constraints from the simpler corners of a programming language, making your design for extensions more complicated because you have to abide by the design constraints from your earlier constraint. But to give a sort of hokey reason why you might be interested in multiple inheritance. One common case this is used is in a sort of mix-in situation. So let's suppose you've got a class that knows how to implement ref counting, knows how to implement intrusive ref counting on an object. And let's say you've got a pre-existing definition of, say, rectangles, right, which doesn't know how to ref count. Multiple inheritance would let you mash these two things together. So you got a ref counted rectangle that is stored still in one object in this situation. So you can combine these two implementations together to get a single class that has both rectangleness and ref countedness. So I said this before, and I'm going to say it again. The way that C++ implements multiple inheritance is to maintain the same implementation strategy that we did for single inheritance, for regular vtable calls. So we're just going to say, okay, well, we need the vtable to abide by we need our virtual method calls to abide by the contract that the virtual method I want to call is going to be at some fixed known offset on the vtable. And we're just going to make this so somehow. And that's how we're going to make multiple inheritance work. So let's take a look at an example of multiple inheritance. So here I have two classes, A and B, and then I have a class C, which inherits from both A and B. And I've drawn out what the object layout for this object looks like. So I've got an A part, I've got a B part, and I've got a C part, and I've smushed them all together, right? Because the C object that contains A and B, well, I need it to have an A and I need it to have a B, and it's going to have a C. So remember that C++ is all about hard coding in offsets, right? So one of the reasons why we're going to maintain an A part is because when we said that we subclass from A, we are giving a sort of layout guarantee that there is some subsegment of the A object, of the C that looks like an A object. So all of my manual offsets for accessing vtable entries and for accessing fields on it work. So when I take my C and turn it into a pointer to an A, which is allowed because C inherits from A, I still point to the start, but I am only ever going to look at the A part of this function. And of course, if I have a non-virtual function on A, then everything works as it did before, right? I just call that implementation if I have a pointer to A. No questions so far, right? Should look very similar. And let's talk about C for a moment. So when I have a pointer to the C object, well, I know more about all of the things that are going on in my object, right? I know about this B part and I know about the C part, and all this is together. C knows that it inherits from A. So if I call this non-virtual function AF on A, all I need to do is I'm like, at the compiler time, I say, well, I want to call AF on C. C doesn't define it, so I'm just going to like find the parent class that defines it. That's A. Remember, this is all happening at compile time. So now that it knows that, oh, this is actually referring to A : AF, I can compile this into a function that passes in the pointer to the C object. But actually, once we get in the function, it's going to be treated as a pointer to the A object because it was defined at a simpler time when we only knew anything about the A. But this is just going to be a no-op, right? Because in fact, the start of the A object and the start of the C object all are the same location. Okay, all okay? We haven't gotten into the tricky part yet, but hopefully this is making sense. Okay, so now I want to look at a different situation. So let's talk about B for a moment. So with B, we have we're going to define a function, BF, on it, and we're going to try to call that function. And when we know nothing about, what's going on in the wider universe of this object, this works just fine, right? So I've got my pointer to B. It points to the start of the B region. I got my function BF, which has some offsets into the fields for B, no problem. And when I call BF, I just go ahead and invoke B : BF in the situation, right? No problem. But what if I have a pointer to C and I want to call the method BF on C? Let's think about this for a moment. So when we were in the B universe, right, and we said, okay, well, my pointer to B is just going to point to the start of the B region. I've got all my offsets ready to go, looking at things inside this B region. Everything is great. And when I was in the C, area, I said, okay, I got my pointer to the start of the C object. That's at the start of A, by the way, right? Because, well, one of the parts can come first. In this case, I put A first. And one of the parts has to come second. That's the B part. So I got my pointer to the start of the C region. And, when I'm just calling functions on C, I know where everything is, right? Because I laid things out. But if I want to call the function BF on B, which is expecting a B pointer, I can't just pass in my C pointer, right? There's a clear problem. The C pointer points to, the A part, and then the B part and the C part. The B pointer has to point straight to the B part. There's a difference. And so to deal with this difference, we have to make our casts have non-trivial computational contact. We need to adjust the cast by a delta to get it from the point where it was previously pointing, namely the start of the C object, to the start of the B object, which is embedded on the inside of the object in question. So stepping back for a moment, right? So I said, hey, the way C++ works, right, is that they were like, okay, we don't want to pay for features if we're not using them, and we want everything to be, as fast as machine code. So when C++ designed single inheritance, they were like, well, we know where all of the fields live, and we have pointers that point straight to the beginnings of objects. So we're just going to compile our functions so that they assume that, the pointer they're given points to the region of memory that looks like a B object, say, and I can just directly do execution on it. Then they wrote this paper about how to add multiple inheritance to the language. And they're like, oh, shoot, when there's multiple inheritance, my pointer to a subclass may not necessarily be the same as the pointer to the parent class. And so what do? Well, if you're JavaScript, you would have been like, okay, well, I'll have some dynamic, hash tables or whatever to like smooth over the difference. C++ was like, no, we are going to add deltas to our casts so that we can just adjust the pointers. And this delta is very cheap, right? It's just an arithmetic operation. We also know exactly what the offset needs to be, because at the point in time we're casting from C to B, we know what the layout of C is, and so we know where the B part is embedded. So this is literally just some integer constant. But it's very surprising for people when they find out that casting pointers in C++ is not always a no-op. In fact, the value of the pointer can change in this situation. Okay, this time I am stopping for questions. Ask me a question. So there's a delta when I cast a pointer. There is a thing I have to do. There's a question, which is, can you manage to overflow that addition somehow? That's a funny question. So let's see. So to overflow the addition, we would need this delta to be so big that it would wrap around the address space. And to make the delta be that big, I would need an extremely large A object. So I guess if you put in, 2 to the 32 fields in your A object, I suppose this will in fact overflow, but your compiler will probably run out of memory before you get there. There's also a question from Twitch, which is the delta of each class determined when defined, or can it be changed later? That's also an excellent question. And so the deltas are basically the offsets between the object layout for the class in question. So the answer then is it's entirely determined statically because, when I'm defining C, I know what all of the subclasses are, right? There's no way for me to say in C++, well, I don't know what I'm going to inherit it from. You're going to figure that out at runtime, right? You know everything at compile time. So I know how I'm putting together all of these parts. And so I can pre-compute all the deltas in that case. You should pay attention, by the way, because you're going to have to implement this in this week's lab, which is about vtables. Okay. So this is just saying the same thing that I said before, which is, so we got this delta, right? So when I do a cast, I add the delta to the pointer in question. Yes, it is overhead, but I didn't slow down, non-multiple inheritance C++ programs, and two, it's very cheap anyway. It's about as good as you can do under the circumstances. By the way, there's also a funny problem that shows up when you allow multiple inheritance, and that is what happens if you have the same method defined in two classes that you're inheriting from, right? So like, we've got a cowboy who knows how to draw his pistol, and you also have a displayable class that knows how to draw itself on the screen. So if you inherit from cowboy widget, and you inherit from both of these things, hey, what's going to happen in this case? And the answer is kind of a cop-out. C++ will just say, well, the method call is ambiguous. So you have to explicitly tell me which one you want in the situation. Just a little aside. Okay, so if you remember, in the previous example, I was only talking about non-virtual methods, right? Those were the methods where I knew exactly where I wanted to go because I just looked at the static class definition and found what the function overload that applied for my situation was. So we haven't talked about virtual functions at all. And virtual functions, we need to do something very similar. So here we go. So we've got a class A, class B, and a class C, defining a bunch of virtual methods. And I am going to inherit from A and B and then overwrite F. And this time, the C++ compiler is going to allow the same virtual function to show up multiple times. So this isn't going to be ambiguous. They're actually going to be the same virtual function in this case. So when I have these pointers, right, C, and they're all objects to C. No matter what pointer I have, if it's a pointer, a B pointer, or a C pointer, when I call F on it, I'm always going to go to the implementation of F in C. Okay, so that's the behavior that I need, which follows from the behavior of dynamic dispatch and virtual methods that we've established already. Okay, so how are we going to do this? Well, let's remember how we implemented virtual method calls because we're not allowed to change it. So the way we implemented virtual method calls was we said that, hey, to do a virtual method call, I'm going to look up the vtable and then invoke a function pointer at some fixed offset on that v table. So if I've got an object named C and I want to call f on it, well, I need to, go look up the v table and then call whatever entry it is for f on the v table. In this case, C::f. Okay. But I've got another problem, which is that when I am pointer to B, I also want to look up the v table and then call a method based on its location in the v table. And so if I didn't actually put a v table pointer at the B part of my object, if I had a pointer to B and then I wanted to call the function, well, hey, the code that I wrote expected the v table pointer to be at a well-known location on the B object. And remember, this is just a B pointer, right? So I know nothing about the A object. I know nothing about the C part. So I've just got the B pointer. And so if I don't know about anything else, I need another v table pointer to deal with this situation. And this v table will hold what B thinks the set of virtual methods are for this object in question. Now, we have another problem, which is that in the example that I gave before, we had C::f, right? Which is the implementation for the function f here. Now, remember we talked about when we were doing non-virtual method calls, if I want to pass a C object into B's implementation, I have to do a delta offset to get the C pointer to turn into a B pointer. So with V tables, the situation is worse. I don't even know whether or not I'm calling into C::f or B::f. I only know that because there's some function pointer stored in the table. But when I'm calling f, I don't actually know. And so when I'm compiling this virtual method call, I actually need to do something, because if I just go the default route where I, define where I just look up the entry in the table and then pass in my pointer directly, I'm going to give it the wrong pointer. I'm going to give it a pointer to B when actually I needed to give it a pointer to C. Sorry, I got it flipped around. In this case, I have a B pointer, but it actually secretly is a C object, and I need to move it to the C pointer in that situation. So I don't know this when I'm compiling this code, right? All I see is a B object, and I think everything is fine. So how the heck am I going to deal with this situation? So C++ cheated. So what they said was, okay, when I define virtual tables, they're not only going to be functions pointers, but they are also going to contain offsets that specify what I have to do differently to the this pointer when I make the virtual call. So now that there is an entry in the V table saying what the offset should be, when I compile this call to f, all I need to do is look at the function pointer at the entry, take my this pointer, and then apply whatever the delta says I should apply as an offset to it. And then that's what I should actually pass to the function in question. And in most cases, that offset is going to be 0. But when you have one of these multiple inheritance situations, that offset will be non-zero. It will actually do something because we need to get it a B pointer looking like a C pointer in this situation. Pausing again for questions. What are your questions? No questions? Well, okay. Let's peep at this slide. So, Okay, I want to contrast this with a different situation where we don't need to actually use the delta offset. So let's imagine that I have a pointer to a C object, and then I call the method G on it. And sorry, we've lost the implementation tons of slides before. But if we recall correctly, C did not define G, B defined G. So do we need a delta in this situation? And the answer is no, because statically, where we say, okay, we want to call G on C, but C doesn't find G. So that means that it's only existing on B's vtable. So all I need to do is I'm going to first cast my PC pointer into a B pointer. That is going to apply an offset. And then I can just call the virtual method as normal. So you'll notice that the virtual table for A and doesn't actually contain an entry for G, right? Because if you are an A, there's no way to actually call G, right? It's not necessary. Okay, let's talk about a few other interesting situations. So one interesting problem that shows up when you try to use multiple inheritance in C++ is the so-called diamond inheritance problem. So what is the diamond inheritance problem? Well, it shows up when you have an inheritance graph that looks like a diamond. So let's just see. So we've got a class named L, that's our base class. A and B both inherit from L, and then C multiply inherits from A and B. And so because we remembered that the rule of C++ is that every object in my multiply inherited object has to look like what the object said it had to be beforehand, there's only one possible way I can lay out this multiple inheritance object, which is that I've got my L, right? I extended it to an A, so this looks like an A. I also got my L and I extended it into a B, and I'm not allowed to deduplicate the L's because if I got rid of the B part, then B would no longer look like a B, right? There would be no pointer that looked like the object layout for a B, which had both an L and a B. And then finally, I add the C part on the end. So the diamond inheritance problem says that, hey, when you do one of these diamond inheritance schemes, it results in 2 copies or as many copies as you multiply inherit it of the shared base class. And this is, once again, very surprising to people who are expecting C++ to work like a normal object-oriented language. But if you're thinking about how C++ is implemented and the design constraint, which is that every any object that subclasses a bunch of other objects has to have memory layout that is compatible with all of those subclasses, there's no other way you can do it, right? You have to duplicate L because otherwise you don't have a valid A object or you don't have a valid B object. Now, how do you fix this? Well, you fix this by changing the expected object representation of the object in question. So C++ is a feature that lets you do that. It's called virtual base classes. And when you have a virtual base class, C++ no longer says, hey, I'm always going to implement it with the L pointer being at some well-known location, and then the L segment being at some well-known location, and the A segment coming right after it. Instead, I'll introduce an indirection. I'll introduce a virtual base pointer, which I have to follow to find the base class in question. And so ordinarily, the base pointer will just point right after the object in question. But if I've got one of these diamond inheritance situations, then the virtual base pointer actually is paying its way because, hey, there's a typo in the slide. The D part should actually read L. It's actually paying its way because to actually use the same L in both situations, all I need to do is have the virtual base pointer point to the same region of the object in question. And of course, virtual base pointers have to be worked out with deltas as well, right? Because if you're expecting an L object, well, when you want to go there, you have to adjust your pointer to actually go to the correct location on the object. So that's what virtual base classes are for, right? They introduce an indirection. It costs you, right? Because you can't access L fields directly. You have to go through this pointer. But as a consequence, you get to deduplicate it, which would not be possible in the fixed object layout. By the way, Haskell has a very similar situation to virtual base classes, and it's kind of interesting to compare them. So if you wanted to sort of model objects in Haskell, the most obvious way to do it is with data classes. And so if I define, say, L, which is my parent class, and then I want to have a copy of L in both A and B, when I write the records for it, which say, well, A has a parent field, which is whose contents is L, and B has a parent field whose contents are L, you can share the same L between the two implementations. And that's because whenever you have a field in a Haskell record, that's actually a pointer to another object. So notice that in the high-level language Haskell, right, you don't get the choice. Well, by default, we insert the indirection for you, right? We assume that you wanted to be able to share L as a normal piece of data in this situation, and so we're not going to force you to like duplicate it in this situation. And so you get this indirection, right? Which is, totally against the C++ ethos, because C++ says, I don't want to pay for anything unless, I actually ask for it. Now, Haskell does have a way of making things a little more efficient, and this is by way of a pragma called unpack. So unpack is a special annotation you can apply to fields in Haskell records, and what it says is don't actually store a pointer here. Instead, store the entire contents of the field in question directly inside the object. That's why it's called unpack, because it basically says unpack the fields of the object, say A in this particular case, into my object. And so now there's no pointer, and you've actually inlined the contents in here, and so you can't share the context. But hey, you don't have to pay for the pointer indirection in this case. And so unpack is a very popular pragma that people writing performance-sensitive Haskell code use, because it does give you some amount of control over how your objects get laid out in memory. So notice the defaulting is very different. In C++, the default is do the fast thing, and then you have to add an extra virtual keyword to get the slow but more sensible thing. Haskell, it indirects by default, and you have to use a keyword to get the performance in this case. By the way, in Haskell, if you had an L object, no way you could get an A object for it, right? Like, which one would it be? And in C++, that's true too. When you have a virtual class, you can't cast from the virtual class to one of its when you have a virtual base class, you can't cast from the virtual base class to one of its subclasses, because C++ has no idea where the object actually lives, right? It could live anywhere. It's just all it knows is there's a pointer there to you, but that's not very helpful if you wanted to do that cast. Questions? What are your questions? Okay. Yeah. So this is what Haskell's code would look like if you devirtualize, if you didn't have a virtual base class, right? We just have two copies of L in both A and B. Hooray for unpack. Okay. So to summarize multiple inheritance, when we implement multiple inheritance in the compiler, we need one vtable per combination of base class and derived class, right? Because every derived class needs to look like that derived class. And so if the superclass had a vtable, then I need to put a vtable in it to satisfy things. And there's a little optimization which we do, which is that, well, the first subclass, the first parent, we can use that vtable to store all of the extra new virtual methods we might have defined in the subclass. So, because in the single inheritance case, right, you just shove everything into one vtable. So that optimization still stands in the multiple inheritance class. But when you have a multiply inherited class, you do have to put in the delta to make things work out. And we can also talk a little bit about what the cost of using multiple inheritance in C++ is. So when you do access members, member accesses on fields, you have to do a cast, right, to get your pointer to the right place before you can actually access the field in question. Then when we are representing the virtual tables in memory, not only do we have to store function pointers, but we also have to store an extra word to store the delta offset that I'm going to apply. And when I do the virtual call, I have to read out the delta from the vtable and then apply it via my ALU to actually get to the correct location. And so one of the funny things about multiple inheritance is you do kind of have to build out this infrastructure, always, because you don't know if a class is going to get multiply inherited from at some later point in time. A member access cost, though, you only pay if you're using multiple inheritance. That's right. C++ couldn't add multiple inheritance without adding a little bit of overhead. On the plus side, there are some alternate implementation strategies that don't have this problem of having to store the delta directly. So some C++ compilers use what's called a thunk. And the idea behind a thunk is that you don't actually... Oh yeah, we talked about thunks in the context of Haskell where they're lazily evaluated values. But in C++, thunk means something a little different. A thunk is just a little teeny bit of function code that knows how to do the offsets before jumping to the actual implementation. So if you can install one of these thunkified method invocations, then you just jump there, you do the thing, and then you jump again to get to the actual implementation in question. Questions? Any questions? Okay. So let's talk a little bit about the big picture for a moment. So we've got all of these object-oriented languages, and I like to classify them into two different types: the dynamically typed languages and the statically typed languages, right? So last time we talked about the dynamically typed languages like JavaScript, which is prototype-based, and Smalltalk, which is class-based. Add to the class-based list, languages like Python, which also have a class system. On the other side of the fence, we've got the statically typed languages. So today, we talked about C++, which is all about inheritance, right? C++ is all about just maintaining the memory layout of the subclasses so that you can write very efficient code. But there's another language, right, Java, which implements objects in a different way. So instead of going the C++ route of saying, hey, we need to be able to ahead of time compile everything to be very efficient, Java says, well, we want a more user-friendly version of the language that is easier to program. We are going to be willing to add some indirections to make our lives easier. And for example, Java supports a concept of interface, where an interface, like C++ multiple inheritance, you can implement as many interfaces as you want on a Java object, but they don't have the same implementation problems that C++ does, because there's actually some level of dynamic lookup going on. And then Java's like, we want to run fast, so we're going to have a just-in-time compiler to make things run fast in that situation. So if I want to compare C++ and Java in more detail, right? C++ is an object-oriented extension of C. Its roots are in C. You can write C in C++. Some people say, hey, C++ has all these object-oriented features. They're bad. You shouldn't use them. But, a template here and there, that's really handy because C does a bad job at those. So some people will write C code in C++. They won't use any of the object-oriented features, but they'll just use templates to make it easier to stamp out generic code. That's cool. Fine. No problem. But Java was designed to be a language that was simpler than C++, so that normal programmers, programmers who weren't obsessively checking over, all of their low-level implementation details could actually write reasonable code in this situation. So similarly, C++, because it's an object-oriented extension of C, doesn't have a garbage collector, right? You're expected to manually manage all your memory. This is one of the reasons why C++ lasted so long as a systems programming language, because sometimes you really cannot deal with a garbage collector. And Java does have a garbage collector, and people spend a lot of time tuning it, optimizing it, fiddling with knobs to make it do the thing you want. C++, there's no such thing. You're on your own. You get complete control over all your memory. And it took like a language like Rust, right, with new ideas about how to do manual memory management to actually give a viable alternative for a systems programming language. C++ is close to the machine, right? We were talking about all these features. We talked about how we do non-virtual and virtual method calls, and I always was saying things like, oh yeah, there's some direct offset that I can compile down to, and we're going to go straight there, and it's going to look very much like the best machine code I could have written in that case. In Java, efficiency was secondary, right? The goal was to be an easy to use language. And so if you had to introduce an inefficiency somewhere to like make the UX a little nicer, Java was willing to do that. And the last part, I'll bundle these together, right? C++, when you run the compiler, it compiles straight to native code. And that, once again, matches with C++'s orientation towards being a systems programming language. So the goal is to write code that is as close to the bare metal as possible. Java doesn't go to a machine code directly. Instead, it compiles to a bytecode representation, which is then actually executed by a virtual machine, which might actually transform it into native code by way of a just-in-time compiler. But the sort of when you compile Java in the traditional sense, it's just going to give you this bytecode. And back in the day, this isn't that common now, right? But one of the like big use cases for Java originally was, hey, you can write Java programs and then run them on your machine without having to trust the person who wrote the app, the so-called Java applets. And the bytecode was a way to make it easier to like ensure that doing so was safe. Now, these days, if you're interested in a sandboxed programming environment, you're not going to use Java. You're going to use JavaScript or maybe WebAssembly. But this was one of the original design goals for Java, and it kind of works. Like you kind of there are enough hooks in principle to do this correctly. Although it's quite difficult securing Java code in general. Questions about this slide? Okay, so I want to talk about the relationship between Java methods and C++ virtual methods. So in C++, we distinguished between non-virtual and virtual, right? We said, hey, you have to say explicitly which one you want, and one of them is going to go into a straight function call, and the other one is going to do this vtable jump. In Java, there's no such distinction, right? This is one of their, I want to make it easier for user programmers to program. So in Java, there's no such thing as a non-virtual method. All methods in Java are virtual. And so if I call f on, this a, which is actually a b, I'm going to get to b's implementation. And what actually happens is that when I compile this to bytecode, it's going to compile into this invoke virtual instruction, which is actually going to go ahead and do the actual call. The other thing I want to point out is that Java supports interfaces, and it supports implementing interfaces. Like you can have a class that implements multiple interfaces. And this looks a lot similar to C++ multiple inheritance. And in fact, if you wanted to simulate Java multiple interfaces, you might try doing it with C++ multiple inheritance. But these are not the same thing at all. In particular, interface calls in Java are also dynamically indirected. So if I have a function, if I have a object C, and I want to call f on it, then sorry, wrong way around. So if I've got a pointer to an object that implements the interface A, and I want to call f on it, once again, the bytecode I get for this case is invoke interface, which does a dynamic lookup to find the actual implementation, which is going to be whatever C's implementation was in this case. And by making this a dynamic lookup, Java interfaces don't have the same sort of problems as C++ interfaces because we don't have to worry about maintaining the same object layout or the same vtable layout. We can just, rely on the dynamic lookup to paper over these differences. So there's no problem where like I either have to put A first or I have to put B first. I'm going to do a dynamic lookup. So like it doesn't matter. Like I'll figure it out one way or another. So one way to like summarize the difference between Java and C++ is that in C++, when you use inheritance, you're making a very, very strong claim about the binary interface your code abides by. A class in C++ is not just a class, but it is a specification of what memory layout your object is going to be. And so when C++ built subtyping with subclasses on top of the classes in question, it was maintaining this interface, this binary interface, this layout, memory layout interface to get things to work out, right? And that's why we had to do all the work with the deltas and with, stamping out multiple copies of the classes everywhere in my program. That's what inheritance in C++ is about, right? So actually, you shouldn't think about it as like object-oriented inheritance. You should just think about it as a tool for like assembling together layouts from smaller layouts to get what you want. And if you think about it that way, you will have a very good time writing objects in C++. In Java, inheritance takes on the sort of much more traditional object-oriented style, which is that, there's no non-virtual methods, everything is dynamically dispatched, so really you can just use inheritance as a mechanism for sharing code between your classes. So like you've got some class, it's got a lot of code that you like, you've got some code that you don't like, you can overwrite it and get a new object. And Java, that's the kind of thing Java inheritance is about, right? So C++ really has this weird interaction with a lot of parts of the language, and that's because of its very strong requirement. Java is giving a less strong requirement, so it's much more, sort of in the classic object-oriented style. Okay, so that's it for all the pre-programmed slides. So C++ said, hey, efficiency matters the most, and therefore we are going to find a simple implementation, a fast implementation, and then the language is just going to have to deal with the consequences. Java was all about, hey, we need a simple language, simplicity matters, and so we're going to think up of what makes sense to programmers and then design our language in that way. So so the difference between C++ and Java. There's a question on Twitch. The question is, by sharing code, do you mean copying the structures in memory? No, that's not what I mean. So it's not about copying the structures. It's just good old-fashioned object-oriented programming, right? When do you use inheritance? Well, one common situation to use inheritance is you've got a class. It does mostly what you want, and you just want to sort of scribble over a few parts, override their behavior to do something different. And inheritance is classically the way you do that, right? Because you inherit from the object, you get all the same behavior, and now you can just override the bits you want to override. Some people would say this is not a very good way of writing compositional software, but there's certainly situations where inheritance is exactly what the doctor ordered. It is like the simplest way to express, how you wanted your software to be written. Any more questions? Okay, I've got 10 minutes left and I've got some bonus problems. So I wanna just do the bonus problems while we are waiting. So here we go. Okay, so our first bonus problem is what happens if I try to implement Java interfaces in C++ by using multiple inheritance? So what have I done? So I've gone ahead and defined an interface A, which defines a virtual method f. And then I've got some class A, which inherits from interface A. And then let's say I've got some interface B, and it inherits from interface, it extends interface A. You can do this in Java. Interfaces can, themselves implement other interfaces. And it adds a new virtual method G, and then I've got some function B that actually overrides G. So does this do what we want it to? Like, is this reasonable code to write in C++? Well, if you don't know, we can just try to write out the object layout and see what happens. So to start off, we've got interface A, right? So that's first object that we've got in this situation. Okay. Then when I define A, that says that, hey, okay, I need to, I'm inheriting from interface A. So I need something that looks like interface A, and then I'm going to have the fields for A. Let me go ahead and define the V. So there's a V table here, right, which contains F. And so this is an object that looks in A, like standard single inheritance situation. Okay. So now I am going to define interface B, and it inherits from interface A. So what is that going to look like? Well, I need an interface A object, because that's what I said I had here. And then I inherited from this, so I have an interface B object, right? And when I look at the V table, it's going to have a V table for F, and then a V table for G. Once again, standard single inheritance situation. No problems. Okay. And now I'm going to implement B, which multiply inherits from A and interface B. So how did we say this works? Well, to actually do this, I have to paste together the memory layouts for A and interface B. Because what did I say, right? I said that every parent class, we need a valid segment of our object to fulfill the memory layout in this situation. So let's put A first, and then let's put B. So we'll just concat these together. And also, I guess, previously this was implemented with A, and then this is going to be implemented with B. And that's it. So that's what the object layout looks like. So to answer my original high-level question, like, does this make sense or not? Well, maybe. So you're like spending a lot of time on the V tables, but you certainly have an object that can look like an A, and it can also look like a B. And assuming interface A and interface B didn't have any fields, it's not really that problematic that you've got multiple copies of them, except you're wasting a bunch of space on V table pointers. So yeah, so it'll work, but it might not, have the layout you kind of were expecting, right? So it's very important, right, when you're doing this sort of thing, to think about what the actual layout you want of the object in memory to be. It's just good advice. There's a Stack Overflow question basically asking this, whether or not you can do it this way. Actually, it's been a while since I looked at this. Let's see. Can I open it? Okay, I don't have internet, so whatever. Okay, bonus problem 2. So what's going on here? I've got just a complicated multiple inheritance situation. So let's just go ahead and slog through it. So we got a class W. Let's call this W. And it's got a bunch of, I don't need to make this so big. It's got a bunch of entries in its V table. So we got F, G, H, and K. Okay. Now I define AW, which virtually inherits from W, and I also define BW, which virtually inherits from W. So let's copy paste this and take a look at what this looks like. So how did we say virtual inheritance worked? Well, it works by indirecting the base of the class via a pointer, right? So what I'll do is I have a pointer which points to, my ASCII art drawing is not very good. Okay, so AW, right? It contains a virtual parent pointer which points to the start of W, and we can. I guess we could define a vtable here. We don't have to. Let's not define a vtable here. And then we override G to be A's implementation, right? And there's also some delta business going on here, right? Because when I call W, what's going on? Yeah, so there's some delta business going on here, which is that when I call W, I need to know how to find the location of A. So this is going to have, like basically delta AW, which I'm going to need for the situation. And sorry about the line mapping. Okay, and we can do the same thing for B. Oopsies. Where we have this vtable, and this time it's going to be F that gets overridden. Okay? So what happens when we put this all together? Well, when we put this all together, because it's a virtual W, I don't actually need to duplicate it. So I'll have one AW and one BW, and they will all point to the same W in question here. And I'm going to override F, and I'm going to override G, and the deltas now have to be a little different. So when I'm at W and I need to get to BW, my offset is as before. I only need to go delta BW difference. But when I'm at W and I want to get to the A pointer, I have to go all the way past the BW and past the AW to get there. So I actually have to do delta AW plus delta BW to get there. And that's what the delta looks in this situation. Questions about this example? All right, we are out of time. Thanks everyone, and see you on Wednesday.